Ugh, discombobulated would be the word for today. Okay, now I'm back. So yeah, I'm making this video in the Tuesday Thursday class. So for the Tuesday Thursday class, today's Tuesday. On Thursday, we'll review for the test, and then I'll open it up for the weekend. Okay. By Monday, Wednesday, I want you guys to watch this one, and then on Wednesday, we're going to review over it. I'm going to send the email out for you to watch it. Wednesday, we're going to go over it, and then we will. I'll open up the test for you guys too to take it, until Sunday. Both of you guys will have it open until Sunday. So it is the last regular lecture per se, or last content before this second test from chapter 2. So are there any questions about any of the previous sections, homework or anything like that? I believe it started in 2.3. So 3, 4, 5, 6. Any questions before we get rocking and rolling today? I'll give you just a second. Okay, so let's start today. Let me get this kind of situated. Laser. Okay. Today we're going over 2.7. Now 2.7 is finding inverse functions. So before we get started, we really have to define what an inverse function is. And there's a very, very basic definition that your book takes 3 or 4 pages to get to for some reason. But the basic definition of an inverse function is when you switch the x and the y's. Okay. So I'm going to give you an example of this just with numbers. If we had 2, 1, 3, 4, -8, 7. Let's say this was our function. Okay, this was our function f. Okay. If I wanted to find its inverse function, now the way we notate it is we take f and we notate it as raised to the -1. Now look, we are not raising anything to the -1. This is just a pure notation thing. Okay. But what we're going to do though is all the y's become x's and the x's become y's. So you just flip these. So this first coordinate would become 1, 2. The second coordinate would become 4, 3. And the last coordinate would become 7, -8. Okay. And that's all it is. You're just flipping x and the y's together. You're kind of reversing the x and the y's. Now, I'm going to come back to this and we're going to dig more on it. But I'm going to start in a different place. But I just want to show you really what this is. An inverse function, all the x's become y's and the y's become x's. It's very, very straightforward. Actually, before I get started, I'll give you an example where we have 2 functions that are inverses. So let's say I had f of x equals 3x plus 2 and g of x equals x minus 2 over 3. These are examples of inverse functions, but I'm going to show you how this happens, or it's kind of neat how it happens actually. So I'm just going to choose a few values for x in the f function. So let's just choose some basic numbers. Let's say this is x, and then this will be the output f of x. So if we chose -3, 0, and let's say 4. I'm just choosing those out of thin air, okay? -3, 0, and 4. When I plug them in to our f function, you'll see if I plug -3 in, -3 times 3 is a -9, plus 2 gives me a -7, right? If I plug 0 in, this goes away, it gives me a +2. If I plug 4 in, 4 times 3 is 12 plus 2, that's 14, okay? So here's 3 random coordinates on this. So this is a straight line function, right? If I graph it, it would just be some straight line out on a 2-dimensional space. Now, but what's neat is if this is an inverse function and I do the same thing over here, and I'm going to change my x values. My x values are actually going to be these y values. So I'm going to say -7, 2, and 14. So if these are inverse functions, what's going to happen is when we plug this x in, -7, it's going to pop back a y value, but that y value is actually going to be the x value over here. So let's see if that happens. If I plug -7 up here, so I'll kind of do it. So if I plug in -7 for g, I get -7 minus 2 over 3, right? So I'd wind up with -9 over 3. Yeah, that's -3. Hey, hey. See that? So the x's and the y's flipped. It's pretty neat. So if I plug in g of 2, well, 2 minus 2 is 0, right? So you get 0 divided by 3, which we know is just 0. 0, 2, 2, 0, neat. And if I plug in 14, 14 minus 2 over 3, so this would be 12 divided by 3. That's just a +4, right? And it happened. So check this out. Like, these are inverse functions of each other, okay? So what happens is for every coordinate, they're going to flip, right? If I had -7, -3 on one coordinate, that means the inverse function, it's going to be -3, -7, and vice versa. Kind of cool, okay? That's all it is. Now we're going to look at these graphically. We're going to look at them equationally, but in the end, this is all that's going on, okay? In the end, this is all that's going on. So first off, let's introduce it equationally. So what happens, or what's kind of neat, if f and g are inverse functions, if f and g are inverse functions, it turns out f composed of g of x equals g composed of f of x, which just equals x, okay? So it doesn't matter which way you do this. When you take the compositions, if they're inverses, you'll wind up with just the x value. So if we go back to that example I just showed you, I told you they were inverses anyway. So right, f of x equals 3x plus 2, and g of x equals x minus 2 over 3. If I take the composition here, which is what we went over in 2.6, right? If I take the composition here, it doesn't matter which way. I can plug f into g or g into f. It doesn't matter which way. It turns out that I'm going to wind up with x because I know these are inverses, okay? But it's a way to check to see if two functions are inverses. So I'm going to think about this one and see which way's easier. I think it's going to be easier to plug this f function into the g function rather than taking a fraction and plugging it into an equation, okay? So if I want to plug f into g, I've got to write it correctly. So if I want f to go into g, that means the f has to come second. G composed of f. Okay, remember, this means I put the f into the g. So I'm going to take this function, I'm going to plug it into the g function. So this winds up being 3x plus 2, that's the x value, right? Minus 2 all over 3. And we'll see if we do this correctly, it turns out that stuff just starts canceling. 2 minus 2 is 0, right? So you get 3x over 3. Hey, the 3's cancel. That leaves you with just x, okay? So because I took the composition and I wound up with x, that means these two functions are inverses, okay? F and g are inverses. I've shown that. Questions out there in Zoom land? Let's find another example of this. I'm going to find it in your homework so we can kind of see how the book asks this question. Ooh. Yeah. So this is number, fractions. Okay. Let's do a challenging one that we really kind of have to simplify a lot. I don't know why I'm doing this to myself, but whatever. Let's say number 8. This is on page 309, number 8. And the question states, Find f composed of g and g composed of f and determine whether each pair of functions of f and g are inverses. Now, I'm only going to do one of them because that's all we have to do to show their inverses. So it tells me that f of x equals, 2 over x minus 4, and g of x equals 2 over x plus 5. Whew. Okay. Okay. Let's think. Okay. Now, is it going to be easier to plug this fraction into here, or this fraction and an integer into there? Huh. I don't think it's easier one way or the other. I'm gonna plug the g into the f though, to show you how to simplify it. So I am gonna do f composed of g, but I really don't think either way is easier for this one. They're both pretty difficult. So let's do that. So I'm gonna take this whole g function, and that's gonna be my x value right there. So I get 2 over, now I gotta pay attention to the big fraction, small fraction. The big fraction is going to be right here. So 2 is the numerator of the big fraction. And then the x has a little fraction in it, right? 2 over x plus 5 minus 4. Okay? So I'm going to simplify that a little bit because I can add the 5 and the minus 4. So wind up with 2 over x plus 1. Okay? That doesn't look anything like x, right? It should. And we got to simplify it to show that it's going to be x. Now you've got to remember a trick here on how to simplify complex fractions. And it's pretty neat. I'm going to kind of break it down to show it to you if you've never seen it before. But it's a really nice way to just get rid of fractions if you have fractions inside of fractions. So you don't have to do this. You can do this in your head if you want, but I want to show you where it's coming from. I'm going to write all three of these parts as fractions. So 2 over 1 over 2 over x plus 1 over 1, okay? And the way you can, the quick way to do this actually is multiply every fraction, multiply every numerator by the common denominator. And now look, there's only one denominator here. So we got a 1x and a 1. So the common denominator, the LCD, would just be x. So what you do is you multiply every numerator by x. We're not violating anything because with fractions, as long as you multiply it by everything, you're fine on top and bottom. So this winds up being, now look, 2x over 1, that's just 2x in the numerator. Now look, check this out. 2x over x, the x's cancel. So you get 2 plus x. This still is not simplifying into an x. Did I do something wrong, guys? I did do something wrong. I wrote down the wrong numbers. Let's go to number 8 real fast. Number 8. Okay, I'm going to fix this one lazily. Okay. This should have been a minus. Instead of minus 4, this should have been a minus 5 here. Okay, which would make this a lot easier. Shoot. Okay, so let's go back. Crap. Okay, let's see. I wrote all this down. Look, okay, I'm going to tell you though why my brain thought something isn't right. Notice from here, stuff isn't canceling. You've got 3 parts of this fraction. You've got 2x, a 2, and an x. Nothing divides evenly into all 3. And so my brain instantly thought, oh crap, no, this isn't working. Because at this point, you'll see when I use the right numbers, things are just going to kind of melt off. Okay. Okay, so let's use the right number. It's not minus 4. That was number 7. If you're looking at the book, it's minus 5. Let's make sure I got the right numerator. Yeah, 2 over x. That's 5, yeah. So I'm going to do the same thing though. I'm going to plug this into here with the right numbers now. F composed of g of x. So this becomes big fractions 2 divided by 2 over x plus 5. That's my x value. But now it's a minus 5 out here, which cancels those 2, which is going to make our life a lot easier. Okay, so this winds up being big 2 over big fraction over these cancel. 2 over x. Okay, now I've only got 2 fractions or 2 numbers in here, and this is a division question. It's 2 divided by 2 over x. And if you remember how to divide fractions, you just multiply by the reciprocal. So this winds up being 2 times x over 2. So 2 divided by 2 over x is the same as 2 times, and then you flip these fractions. 2's cancel, and you wind up with x. A lot easier, okay? A lot easier. I was right, though. This is how you do simplify a more complex fraction. I want to have that in the bag of tricks, okay? Question. So again, this is showing that these 2 functions are inverses of each other. So if I plug like 5, numbers into this one, I get back y's, it'll be the opposite over here for this g and the x's, okay? Okay. Ugh. It's always fun when you mess up something. So now let's go, well, how do you find if a function is an inverse? And before I can really get to that, we've got to talk about one-to-one functions. It's really one-to-one relations, but we can call them one-to-one functions if we want to, okay? Now, remember a function, if we go back to how we defined it on the last test, it's just that the x's couldn't repeat, right? One-to-one function, now look, we can write this as 1-1, so we don't have to write out one-to-one. A one-to-one function is really a function that just doesn't have any repeating x's or y's. Okay, so if we looked at, like, let's say some coordinates here, like 1, 2, -3, 4, 2, 7, and 0, 4. If I asked you, hey, is this a function? You'd say, okay, yeah, well, let's look at the x's. 1, -3, 2, 0. Yeah, this is definitely a function. But if I ask you if it's one-to-one, the y's also can't repeat. And we'll notice we have repeating y's here. We got a y equals 4 for both of these. So this example is not one-to-one. Okay, this is not one-to-one because the y's are repeating. Okay, the y's are repeating. So if we looked at an example just with coordinates, that's one-to-one. Like that very first thing I wrote down today. Was it 2, 1, 3, 4, and -8, 7? This was that f value that I told you about earlier, right? Notice the x's don't repeat, 2, 3, -8, and the y's don't repeat, 1, 4, and 7. Okay, so because the x's and the y's don't repeat, this is a one-to-one function. And the reason we need it to be one-to-one if we're finding inverses is because, remember, the y's become x values, okay? So if a function's not one-to-one, when you make that switch, like if we made the switches for all this first example, let's call it the g function here. This g function, if I tried to find its inverse, it wouldn't be a function. We'd have repeating x values for this coordinate and this coordinate, right? So that's why the functions, if they have an inverse, I should say, I'm gonna write this down. If a function has an inverse, then it must be one-to-one. Or you could kind of write it as for a function to have an inverse, it must be one-to-one. That's another better way to say it. Okay, it must be one-to-one if it's going to have an inverse. Okay, not all functions. Look, this g function, this is a function, right? This is g. It's a function. It's not going to have an inverse function though, because the x's are going to repeat because those y's repeated. Down here though, we know this does have it does have an inverse, right? When we flip them, look, none of the x's now repeat because none of the y's repeated earlier, okay? So therefore it's 1-to-1. Now, here's the issue though, or not the issue, but we also have to understand that it's not just a vertical line test now. We also have a horizontal line test for 1-to-1. So we've got a horizontal line test. I'm going to say horizontal and vertical. For a one-to-one function. Okay, put my mask on. Slides off. So horizontal and vertical line test for a one-to-one function. So just some examples here that would be one-to-one and would not be one-to-one. Let's say we looked at kind of the square root parent function. Okay, looks something like that. Look, this would pass the vertical line test, right? If I drew a vertical line anywhere on here at any point, it's only going to cross once. And it would also pass the horizontal line test, right? If I draw a horizontal line test anywhere on here, it's only going to cross once. So this is a one-to-one function. But a parent function that I know is not one-to-one would be like a quadratic. Remember the quadratic function looks something like that, right? Passes the horizontal line test, no big deal. It is a function. But look, if I drew a horizontal line, I'm sorry, vertical line test. But if I drew a horizontal line at any point, it's gonna fail it because it crosses more than once. So it's not one-to-one. Okay, a quadratic is not a one-to-one function. Quadratic and like absolute value, same thing, right? Remember how the absolute value function looked? Look something like that. That's not one-to-one, right? Because if I drew a horizontal line, it would cross more than once. Okay, so this is one-to-one. So what a one-to-one function means is the x's and the y's don't repeat. It also means that when you graph it, it has to pass the vertical and the horizontal line test. And for a function to have an inverse, like the quadratic and the absolute value just don't have inverses unless you do some real funky stuff with them. They just don't have inverses. Okay, the square root in a weird way does, but yes. So for a function to have an inverse, it must be one-to-one. Okay, so let's find inverses now. And then we'll check them with that composition, okay? So how do you find an inverse? So first off, I'm going to steal some straight from the book that are kind of, not, I won't say they're easier, it's just straight from the book. This is number 16 in your book. 16 says f of x equals 3x minus 1. And the question states, this is 16, states A, find an equation for the inverse, and then B, verify your equation by showing that the compositions are equal to x. I'm just going to do one of the compositions. Okay, so 3x minus 1. So here's how you do this. And I'm going to write the steps down as I'm finding the inverse. The first thing I'm going to do is write f of x as y. Okay, it'll just make it easier for us moving forward. So the first thing I'm going to do is just write it as y equals 3x minus 1. Okay. This is find. I should write this down here, right? Finding inverses. We verified the inverse, but now we got to find the inverse. Okay, second step, we're going to change the x's and the y's. Remember, the inverse of a function is just that the x's and y's switch, right? So therefore, now we're going to switch the x's and y's. So if you see an x, you're going to write a y. If you see a y, you're going to write an x. So this is step 2. So and that y right there is just going to turn into x. Now look, it's almost just like I'm deleting it and writing an x. Deleting it and writing a y, right? Okay. So step 2, you switch the x and the y. And then step 3, you're going to solve for y now. That's going to be your inverse, actually. So solve for y. Add the 1 to the other side, and I get x plus 1 equals 3y. And then I'm going to divide the 3. And okay, I'm going to do this a little differently. You could just divide everything by 3, and that's fine. But I'm going to divide all parts by 3 to kind of graph this in a second to show you what it looks like. But in the end, we wind up with y equals, this goes away, x over 3 plus 1/3. Now I'm going to clean this up a little bit. Now look, this is your inverse function. So step 4, this new y is actually your inverse function. So we're going to write it as such. So it's f inverse of x equals, now I'm going to write this as 1/3 x plus 1/3, because x divided by 3 is just really 1/3 x. Okay. Questions? So that's a step. Now, step 5, we're going to check by composition. Check by composition. So any questions, though, we know how to take compositions. So step 1, I just write the y. Step 2, I flip the x and the y, and then I just solve for y here. Okay, the hard part really is solving for y. So I'm going to check this now. Now, look, I think this will be a little easier to plug f into the inverse here. So I'm going to check. This is me checking. I'm going to plug f into what I believe is the inverse, okay? So I'm going to take this whole thing and I'm going to plug it into that x value. So it would be 1/3 times 3x minus 1 plus 1/3. Okay. Distribute the 1/3 and I get, well, 1/3 times 3 is just 1, so that cancels. So losing with x minus 1/3 plus 1/3. There we go. These cancel, leaves me with x. So I know that these are inverses. So that is my inverse, 1/3 x plus 1/3. Kind of neat. Okay. Questions out there in Zoom land? Okay, I want to graph this. We're going to come back and do more examples of this, okay? But I want to graph these two to show you what's kind of neat about inverses on a graph, okay? So remember, this function was f of x equals 3x minus 1, and the inverse was 1/3 x plus 1/3. So I'm going to graph both of these. Try to get it as symmetrically looking as possible. So the first one is minus 1 So if I graph this first one, it's going to be at minus 1, and I'm going to go up 3, 1, 2, 3, and then over 1. It looks something like that. Okay. The other one, I'll use this pink marker for the other one. We've got the y value is 1/3. I shouldn't say the y value. The y-intercept's 1/3. And then we're going to go up 1 over 3. So up 1 would be about right there. And then over 3 is about right here. So it looks like that. Okay, so it turns out inverses on a graph, which we know these are inverses. We checked them already. They're always symmetric around y equals x. There's that y equals x line. This is my messed up marker. Yeah. Can I make it from here? Let's see. Nope. Oh, I'll get that. That's my y equals x line, right? And it turns out inverse functions will always be symmetric around that line. It's also true for those coordinates. Like, let's make up some that are a little easier to graph. Let's say I gave you just coordinates for a function. Let's say like -2, 3, 4, 6, and 0, 2. Okay. Now this is a one-to-one function, right? The x's don't repeat and the y's don't repeat. So the inverses, now we'll use a different color here. Let's use the pink so it kind of pops a little bit. This will be 3, -2, right? 6, 4, and 2, 0. The y equals x line is just, it's the line we're symmetrical on. Let me show you. It's because the slope is 1 and the y-intercept 0. Let me show you on this next one. So if we wanted to graph these two coordinates kind of separately, but on the same graph, like we just did. So I think -2 is the furthest image this way. 6, 2, 3, 4, 5, 6, and then to the right, 6, 5, 6, and then down, -2. Okay. So I'm going to graph the black coordinates first, right? The original function's coordinates. So -2, +3. But I want you to see something that's kind of neat. When I graph really the inverse coordinate for this, 3, -2, notice it is symmetric around this line, okay? This is the line y equals x. If we graph the line y equals x, it would look like this, okay? Whoop. That's the line y equals x, okay? Origin 0, or the y-intercept 0, and then the slope is 1. So let's do the next coordinate. So 4, 6. 1, 2, 3, 4, and then up 6 is up here, right? And then 6, 4. 1, 2, 3, 4, 5, 6. 4 is right here. Notice they're symmetric around this y equals x. And lastly, we've got 0, 2, and 2, 0. Again, symmetric around. Look, I mean, these weren't meant to connect, but notice that these three coordinates, that one doesn't look pink, but it is. Look, these three coordinates are symmetric around these three coordinates around this y equals x line, okay? If we folded the graph on that y equals x line, they would be on top of each other, okay? And that's what happens. So it turns out inverses are symmetric. I'll write that down. Are symmetric. Inverses are symmetric around y equals x. Inverses are symmetric around y equals x. Let me get this kind of in focus a little more, guys. It's going all over the place. Weird. Okay. Okay, let's go back now, though, to finding the inverses. Back to this stuff, finding the inverse stuff. I know that was kind of tangential, but it goes along with checking them. So let's go back to this. Let's go back to finding inverses. I'm going to give you one, and I want you to try to find the inverse. Do those steps that we wrote out earlier. I'll steal one from the book. It's not a big deal. We'll do another linear example. Actually, no, we won't do a linear example. I want you to try one that's cubic, actually. So this is number 18. 18 says f of x equals x cubed minus 1. So I want you to find the inverse of this. Now, if you want to go back, here's the steps right there. So find the inverses for this example. If you don't get it right, that's fine. I mean, I'm going to go over it. I'm not going to leave you hanging. Okay. Let's run through this one. I'm going to go through the steps. I'm going to have to keep it up here. We go through the steps as I go. So first off, I'm going to write this as y equals x cubed minus 1. And then I'm going to switch the x and the y. So this becomes x equals y cubed minus 1. Okay. And then I've got to solve for y now. So if I've got y cubed, if I've got an exponent, I need to solve for it. And you haven't seen this in a while. All you have to do is isolate the exponent. So we get the 1 to the other side. And then we take the cube root of both sides. Now look, if it was a square root, we'd have to attach a plus or minus. Doesn't matter with the cube root, okay, because it's odd. So I've got to take the cube root of both sides. And then what happens is this cube root and this cube cancel. So I wind up with a cube root of x plus 1 equals y. Now, once I've got y solved for, I can write that as the inverse. It should be the inverse. We'll check it. Of x plus 1. Okay, so called this y, switch the x and the y, and then solve for y. That was all this stuff. And then once I get y solved for, that's just the inverse. Now, I'm going to check it by taking the, no, this is the check part, right? I'm going to check it by composition. So I'm going to plug this into here. So I'm going to plug the inverse into the f. So f composed of f f composed of the inverse. So when I do that, I'm going to take this and plug it into here. So it winds up with the cube root of x plus 1 cubed minus 1, right? This is our new x value. The cube root and the cube cancel. So you're left with x plus 1 minus 1. You're left with x. So it shows that these are inverses of each other. So that is the inverse of what we started with. Now I'm going to graph these two. One, because it's a good review of the transformation section. Was that 2.5? But also it's going to show that it's symmetric around y equals x. Okay, so let's graph these two. So first off, the x cubed minus 1. So if I wanted to graph that, remember the minus 1 means we go down 1. The x cubed function, so if I put in 1, I'd get back 0, right? Yeah, the x cubed function looks something like this. Okay, there's the x cubed function. So that's f. Now let's graph the inverse then. I'll use the pink to graph the inverse, okay? The plus 1, now it's on the inside of the function, so that means it goes to the left 1 unit. Put in 0, I get back positive 1. It's something that looks like this. Probably dig down a little bit further, that's fine. It's something that looks like that. And notice, so that's our f inverse function. And notice that these are symmetric around each other, around y equals x. Right? There's that y equals x line again. I know it's not perfect because I'm drawing it by hand, right? But pretty dang symmetric around the y equals x line. Kind of neat. Okay. Questions? So we found the inverses. We've checked it. That's actually another part in the homework. And then we've graphed them, which is kind of neat too. Super neat, actually. Okay, I'm going to do some now. I'm going to give you, let's see. Oh my gosh, man, they really throw some crazy ones out there. Let's do a crazy fraction one just to see how much simplifying goes along with it. I want you to try it. Try it. Test your skills. Okay, see how your skills are before we get there. This is number 26. Guys, this is again on page 309. It says f of x equals 4. Let me get the fraction right this time. 4 over x plus 9. So again, I want you to find the inverse and then check it, okay? We won't graph these. These are kind of crazy to graph. But let's find the inverse and check it. So A, find the inverse, and then B, check it with the composition. I'll give you a little time. This will take a little bit of time. Okay, let's try this one. This is going to be testing. Okay, so first off, I'm going to write this as y equals 4 over x plus 9, right? And then I'm going to flip them. So x equals 4 over y plus 9, right? Now at this point, we've got to get that y solved for, right? But it's in the denominator. We can do a few things. First off, let's move the 9 over. Why not? So I'm going to subtract the 9. So I get x minus 9. X minus 9 equals 4 over y. And then to get the y out of the denominator, I can multiply both sides by y. Right? So I get y times x minus 9. I don't know why I keep wanting to say x plus 9. X minus 9 equals, now these y's cancel. Leaves you with 4. And then I'm going to divide x minus 9 on both sides. And I'm left with y. Why do I keep saying x plus 9? Y equals 4 over x minus 9. That's kind of crazy. So first off, to do this, I didn't get the y by itself, I got the fraction by itself. So I moved the 9 over. Then when I wound up with x minus 9 equals 4 over y, I multiplied the y to the other side. And then I just divided off everything that wasn't a y, the x minus 9. So you wind up with our inverse function, 4 over x minus 9. Okay. Then I'm going to check this. So, oh, I think it'll be easier if I plug the original into the inverse. So I'm going to plug the original function into this inverse function. So it's going to be 4 divided by 4 over x plus 9 minus 9. The 9's cancel, so you get 4 over x. Then we're going to do the same thing we did earlier. That's 4 times x over 4. These cancel, and it leaves you with x. Okay, we did this. This was that example earlier that I messed up on and had to correct it just like it, okay? So it turns out this is the inverse function. Okay, it took a little work, but it did wind up being the inverse function. Question. Took a little more work because it's fractions, right? And I'm not saying you should really expect one of those on the test, but it's a good challenging example. Okay. Great. Okay. Let's look at some graphing ones now. This is number 36, and I want you to try this. 36. It says in exercise 35 through 38, use the graph of f to draw the graph of its inverse. To draw the graph of its inverse. Okay, so we've got this going on, right? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now look, 36, it really gives us 3 coordinates, right? And I'm going to write those coordinates down. The first one is -3, 0. -3, 0 right there, okay? Then it gives us -1, +2. Now that's a +2. -1, +2 right there. And then lastly, it gives us 5, 3. So 1, 2, 3, 4, 5, and then a +3. Now, the difference between this one and the one I did earlier is it connects the dots for us. And it looks like that, okay? And notice this function is 1-to-1, right? It would have, it would pass the vertical and horizontal line test. So then it asks us to find the inverse function to see what it would be graphed as. And look, I would use those 3 coordinates and I'm just going to flip them now, right? So the inverse function, well, this coordinate would be 0, -3, right? So 0, -3 would be right here. -1, 2, well, that's going to be 2, -1. And then 5, 3 becomes 3, 5. So 3, and then at 5, 1, 2, 3, 4, 5. And notice it looks something like this, which is kind of neat, right? And notice it is symmetric around the y equals x line. Some algebra stuff going on. Symmetric around y equals x. Okay? So I just want to do one like that because it's a little different. Okay. Do you guys have any questions? I'm going to assign the homework. We're done a little bit early, but I don't mind staying here and you asking any questions. So let me give you the homework. So page 309, section 2.7, right? Numbers 1 through let's say 1 through 21. Then we're going to skip 21 and do 25. Then 29 through, these are all going to be odd, guys. size. So 29 through 39. 45, 47, 53. Now these last ones are pretty neat, and I'm going to probably go over them a little bit in review because they're kind of the next level. Like once you get the homework done, then try these 53 through 63. They're a little different. And then that's it. Okay, that'll work. So these are all odd. I'm gonna stick around for a little bit. If you want to ask questions, you're more than welcome to stay on here. I'm gonna stop the live feed so the video's not too long.